Okay, next we're going to look at two-point perspective and see how it differs from one point. In two-point perspective, you're going to have more than one set of lines receding from the picture plane. So, in other words, if you imagine a picture plane that's parallel to this wall and thus parallel to the front of this box, I'm now going to turn the box so that neither these lines nor these lines are parallel to the picture plane anymore. The verticals, if I hold the box vertical or if it's sitting firmly on the ground, the verticals are still parallel to the picture plane. They'll run north and south forever, but those are the only ones we're going to get for free in two-point perspective. Let's see how that works. When you're looking at something that's sitting on the ground in two-point perspective, you're usually going to see that there are some angles there. They may be more or less dramatic, but that's by definition. Those, if it's in two-point perspective, there are going to be some angles at the bottom. So instead of having a whole face of your box parallel to the picture plane like you did in one-point perspective, you're just going to have one edge of the box that is parallel to your picture plane. So if I imagine my picture plane going like this now, because I'm facing my box this way, I just have this line this vertical line parallel to my picture plane, and the other lines are receding from it. So I could draw the near edge of the box like this. And I'm just arbitrarily, oops, I kind of made a double line there. Let's just make a double line. There we go. I'm trying to make it nice and vertical. I'm arbitrarily putting that box a certain distance below my eye level and making it a certain size, just to show you how this works. When I look at this angle here, I'm going to make an angle. What is that angle? That angle shows how fast this line, if I were to extend it, recedes to eye level. In other words, it shows me where that line has its vanishing point, and where every other line that's parallel to it has its vanishing point. This angle is hard to read, right? But I have to read it in order to find out where the vanishing point is. I have to read one of them. There are several lines. I'm drawing this line here, which you can't see. It's parallel to this one and this one. I have to pick one of those to tell me where the vanishing point for all that set of parallel lines is on eye level. I find it easiest usually to pick the one that's on the floor rather than this one or this one, but you may find that your results differ. So you decide. What I do in my mind is I put a clock face on it, and I say it looks like it's about 2 o'clock, that angle. I have to do something to kind of flatten it out so that I see it as a flat shape. So I'm going to say that that angle looks like that, and I'm going to say that this angle looks a little bit steeper. I have a very steep view of this box because it's so close to me and so far below me. So I'm going to say that this angle is a little bit steeper and it hits the eye level line right about there. Okay? So I have one vanishing point here and one vanishing point here, fairly close together. I can reach both of these vanishing points, which is an unusual situation because this box is so close to me and to my picture plane. If this is the top of that near edge that I drew at the beginning, and if this is the vanishing point for these parallels, that means there's only one place that this line showing me the top of the box can go. It has to go to that vanishing point because it's parallel to this line by our rule. And there's only one place that this line can go from the top of this box. It has to go to that vanishing point by our rule because it's parallel to that line there. I'll put one stroke through these parallels so that you can see the set. Now I get the verticals for free, so I'm going to say here's a vertical. This is where the box is going to end. This again is just good drawing, right? If I get it right, it's a good drawing. If I get it wrong, it's a bad drawing. But this linear perspective will not help me. With those lines, I have to make a drawing judgment about where those verticals go. But once I have established a place where that vertical line touches this line that goes to the vanishing point, then there's only one place that that line can go. It's going to be parallel to these two, so it has to go to the left vanishing point. If I get really lucky and I hit it, there we go. And there's only one place that this line can go that cuts off that side of the top of the box. And of course, that's to this vanishing point. Right? So there we have a box that is slightly smaller in the back than it is in the front on both sides. This dimension here is going to be a little bit smaller than this one. And this one is going to be a little bit smaller than this one because these are further from the picture plane. So linear perspective helps us codify and kind of scientifically nail the thing that the lenses of our eyes do for us, which is they curve the light rays somehow so that the things that are further away from us actually appear a little bit smaller. It's a limitation that is very, very useful, like many limitations, but it's also a little bit of a fake, right? Because it's telling us that the back of the box is smaller than the front, and it really isn't. So if you've ever seen an isometric drawing, you've probably done this isometric drawing here. I always used to do this drawing while I ate my breakfast when I was a kid. You take two squares that are just as close to the same size as you can make them, and you simply connect their corners. And if they were exactly the same size, those would all be exactly the same angle. And you have a box that is, I made my box a little too big, but you have a box that should have been exactly as big in the back as it is in the front. We call this isometric perspective. Isometric, meaning same measure, because it shows us what's true in real life, which is that the back of the box is the same size as the front. This shows us what we see in real life, which is the back of the box is smaller than the front. So most people find this sort of drawing more realistic because it shows us what we really see. Engineers, architects, people who are putting together IKEA furniture find this kind of drawing very useful because it shows us the world as it really is, where the back of the box and the front of the box are the same size. So this is the theory behind two-point perspective. I'm going to erase isometric here because we're not concerning ourselves with that today except to contrast it with linear perspective, which follows the rule of the vanishing points. So just a couple more things about two-point perspective. This gets a little bit more complicated than 1 point, actually. There's a lot of information in these vanishing points, just like there was in the 1 point vanishing point. The distance between the vanishing points gives us an idea of how far away the artist was from the thing that she was drawing. So if you draw an object in your drawing that has its vanishing points very, very close together, it's going to make it look like you were really up on top of that thing, like it was very, very close to your picture plane. If you draw an object that has its vanishing points way the heck out in the hallway and down the hill, it's going to make it look as if you were a mile away from the thing that you're drawing, and it's not going to have these dramatic recessions to vanishing points that my drawing has here. So the moral of that is that when you're drawing from real life, vanishing points, of course, will move. This box is going to have different vanishing points from a box that looks like this, right? Because they're not, it's lines that recede from the picture plane are not parallel to each other, so they're going to need vanishing points. But they need to be a similar distance apart from each other in order to give the viewer the feeling that you, the artist, were looking at them from approximately the same distance. Let's do one above eye level just to demonstrate that point. So I'm going to make this one, because its sides are not parallel to this one, oddly, I'm going to make it vanish to a point right about there. And that means I'm going to have to move this vanishing point down here so that it vanishes to one about there, because I want to keep these more or less the same distance. Whoops, let's lower this one a little bit so that I can have the same distance. Something like that. Okay, so there's one, and there's one. So this vanishing point is going to work for this side. This one's going to work for everything on that side. I'm going to arbitrarily cut my box off here and here, say. So this one will work for that one. This one will work for that one. There we go. And there's my box. I'm going to make these dotted lines so you can see it a little better. We can see that the box is above our eye level because it's got, because we can see the bottom of the box. We can see that it's turned a little bit from this one. In other words, this face and this face are not parallel. We can tell that by our rule. If they were parallel, their lines would meet at a vanishing point, and they don't. They meet at two vanishing points that don't quite match, right? And this is a case that you run into much more frequently in real life, where objects are all cattywampus from each other. They may not be lined up with the walls of the room or anything else. They're at all different angles to your picture plane. In two-point perspective, the only thing you get for free is the verticals. Everything else needs a vanishing point. Only lines that are parallel to each other may share their vanishing points. And if they're parallel to each other, they must share their vanishing points. So this is how two-point perspective works in theory, and we'll look later on at how you find these vanishing points in